All right, so we talk about groups and discrete logarithm problems and so on. So it is a good time to talk about elliptic curve cryptography, because here we are going to define a group and the group operation using the points on the elliptic curve as group elements, and we will define a very strange addition operation which actually will give us a group operation. So an elliptic curve is just a curve defined like this equation, like y squared equals to x cubed plus ax plus b. So a and b are just constants. If you just choose it like this, the picture of the elliptic curve changes. So, but generally it is something like this or this, okay? So let's focus on one of them, of these pictures, and show how these points actually can be used as a group. So points on an elliptic curve generates a group where the points are the elements of the group. The addition of 2 points P and Q is defined as the point as follows. Draw the line that passes through P and Q. It intersects the curve at a third point R. Multiply the y-coordinate of R with -1. So you are actually taking the reflection with respect to the x-coordinate. The resulting point is P plus Q. Identity element is a point at infinity, which is at the top of y-coordinate. And it is defined like this. So assume that there is a distant point very far ahead on the top of this picture, okay? So we show it like this. So if you go in this direction, there's a point there at the infinity, which we denoted by this notation, okay? And actually here we are drawing the elliptic curve in real numbers. So this is in R2. So if you use some other notation, that point at infinity actually makes a lot more sense. But let's focus on the addition operation I mentioned. So I want to add P and Q, right? So you draw the line. Due to the definition of the elliptic curve, it has to intersect the curve at the third point. So it is this. Just take the reflection with respect to x coordinate here. And we say that this is P plus Q now. So very strange way of, I'm not adding coordinates here, right? I'm just drawing a line, intersects them, and obtain this point. So this way, I actually have a way of adding a point to itself. So if I want to add P to itself, I draw the tangent line here. It intersects the curve at a second point, and I take the reflection, and now I ended up with 2P. So as you can see, this is how I'm going to describe elliptic curve discrete logarithm problem, because now I can at this point and this point, right? I can draw the line. It has to intersect at some point, and I will go there, and now I will call it 3P. 4P and 5P, you can add it to itself, or you can add 2P to itself, like drawing the tangent here, and obtain the 4P. Okay. So our discrete logarithm problem will be choosing this number versus D. Add the P itself D many times and obtain a point versus here, and use this as the public key and use D as your private key. And that point actually in cryptocurrencies is the wallet address that you transfer the money to, okay? The coordinates of such a point actually is hashed, some checksums are added and so on, then converted into some representation. And whenever you are actually sending money to a cryptocurrency wallet address, you're actually sending money to a point on such an elliptic curve. Okay. So we mentioned that every element should an inverse in a group. So here the inverse is this. So for a point P, the inverse is at the reflection here, because recall that if you draw the line here, it goes to infinity, right? So this is why we say that there is an identity element in the infinity. So minus P plus P, it goes to infinity here. Okay. So every element has an inverse. We have the addition like this, and we have the identity element. Okay. So since there are infinitely many points here, for instance, for this elliptic curve, we define it over R, real numbers. So there are infinitely many points. But again, as I mentioned, I want to represent finite data with this point. So I look at this elliptic curve over some group or field like Z89 here. Okay, so elliptic curve crypto systems were invented independently by Neil Koblis and Victor Miller in 1985. So since then, we are using this cryptography. So Your wallet addresses in cryptocurrencies are actually points like this. Okay. So let me show you a very basic example so that we can visualize. So let's focus on an elliptic curve over F23. Okay, so I choose my prime number as 23, and I consider the elliptic curve y square equals to x cubed plus x plus 4. Okay, defined over F23. So I choose my constant a equals to 1, and here I chose my b equals to 4. In order for this to be an elliptic curve, this equation modulo the prime should be different than 0. Okay, so in this case, it is different than 0. So we know that this is an elliptic curve, so you can use it. So there are 29 points on this elliptic curve when you restricted it to F23, because now coordinates has to be something between 0 and 23, right? So these are the points. So this means that these values actually satisfy this equation. So if you take, for instance, x equals to 0, you end up with y squared equals to 4. So y can be 2. Y can also be minus 2. But there's no minus 2 in Z23, but we have 21 instead, right? Because minus 2 in modulo 23 is actually 21. This is how you obtain the point, and there's also the point at infinity. And group operations, I explained them as, in a sentence saying that, draw the line and take the reflection and so on. But actually, if you want to do it in an implementation, this is how you add P to Q with this formula. So coordinates of P is x1 and y1. Coordinates of Q is x2, y2. So the summation will give you a point with coordinates x3 and y3, and these coordinates are calculated like this. Of course, there's a division here, but since we are not going to work on real numbers, but on a group, this division actually, multiplying this number with this inverse, okay? So this is not a, these numbers are not, this division is not division, but, multiplication with an inverse. So if you want to add P to itself, then the formula changes because we don't have x2, y2 here. Instead, we have the same point. So this is the formula. So these are they are very efficient implementations of these algorithms. This is why actually we use it. So here's an example for a generator, for instance. For this elliptic curve, this point actually generates the whole elliptic curve. So if you add P to itself, it ends up to be this point. Add 2P to 1P, you end up with this point. So if you go back and implement these formulas, you can verify your implementation by checking these calculations. Okay. At the end, you end up with the point of infinity. So this is why you have 29 points on this elliptic curve. Okay. So let me finish this part by giving an example. Bitcoin's elliptic curve is SECP 256K1. Bitcoin uses this elliptic curve as it is defined in Standards for Efficient Cryptography, SEC. So Satoshi deliberately chose a standard which is not included in NIST standards, okay? Because some people at the time scared that NIST or NSA, actually not NIST, might put some trapdoor or backdoor inside this algorithm. So Satoshi deliberately chose some other standard, and it is this elliptic curve. So that elliptic curve is defined like this: y squared equals to x cubed plus 7. And it is defined over fp, where p is a very large prime number, and it is like this 2 to the 256 minus these small values. And you end up with a prime number like this. So all points on this curve are valid Bitcoin public keys, and this prime number P is like this in hexadecimal notation. So these subtractions actually end up with these differences here. Okay. Base point G is this. Okay. So everybody is actually using this base point G. So whenever you create a Bitcoin wallet address, actually you choose a random number D, add this point G to itself D many times, and the resulting point is your public key, public wallet address. And this order of n of this point is this. Okay. So this is one of the most used elliptic curves in practice, because since Bitcoin included this elliptic curve and elliptic curve arithmetic as libraries, almost every following cryptocurrency like Ethereum also use this. So Ethereum wallet addresses are also generated from this elliptic curve. So for this reason, NIST, I think this February, a few months ago, in other words, added this elliptic curve to its standards, to the appendix of their standards, actually saying that, since everybody is using it for interoperability, we also included it here. There's no need to use this curve instead of a NIST curve, but we wanted to add it so that for interoperability, people might use it.